You're here because you want to master reaction kinetics with a University of Cambridge graduate. Let's begin. Reaction kinetics is one of those topics that I feel is the most application heavy, where you don't really have to memorize too much for this topic, but you need a lot of practice in order to get things right. So to start us off, we have to know what is the rate of a reaction. Well, the way we measure the rate of reaction is to understand that it is a change in concentration of either a reactant or a product per unit time. So it's important for the question to standardize this, and you also have to standardize your answers according to the context of the question. Now, when we deal with rates, there are many different kinds of rates, and it is also important to know what the question is asking, whether it is either the instantaneous rate, which is the rate at a very specific time. So for example, they'll tell you at t, which is time, equals to 10 minutes, what is the rate at that time? And then you have to measure the rate at that time using whatever information you have. Or they could be asking for the average rate, which is the change in concentration of a reactant or product over that time interval itself. Or it could just be the initial rate, which is when time equals 0, what is the rate? And here you can see two graphs that demonstrate this pretty well. So let's move on to the rate equation. The rate equation essentially comprises of a rate constant, which is K, and your reactants, which here we will just say A and B, in a reaction where A plus B gives C plus D. So these two would be the reactants. And M and N are the orders of each reactant. So this jumps to my next point about orders of reaction and reactants. So for the orders of reactants, it is pretty much how much the reactants have an influence over the rate. In a sense, it is the proportionality constant. And for the order of your reaction is the total orders of all your reactants. So this is the orders of all reactants itself. And I'll get more into that later on. And as for your rate constant is constant for every specific reaction and at a specified temperature. So if we look down over here, this is a good summary of the different orders of reactions and what are the different graphs that you have to take note. So do take note that for each graph itself, I don't really want you to memorize the graph. I want you to apply your knowledge on orders of reaction in order to attain the graph. So please take note, these are not really for memorization. The reason why I say you do not want to memorize this is because every question is different in its own sense, and if you just memorize and try to fit the graphs into the question or into whatever context you're given for that question, you're most likely not going to succeed. So in that sense, I want to help you apply the concepts of orders of reaction and see how you can attain the graphs from there. Let's start with zero order. So if a reaction is pretty much A to give B, so if the order of reactant A is 0, this means that the rate is not proportional or influenced to A itself or the concentration of A, and therefore whenever I try to increase the concentration of A, the rate will remain constant. Pretty straightforward, right? Now we look at a concentration and time graph. So if I have a reactant versus time graph, if we look at the trend, it's just going to go down because as time passes, my reactant will proceed to decrease and decrease in concentration as the reaction proceeds. But then the gradient is constant. And from here, in this graph, the gradient is equal to the rate. Now we go on to first order. So for first order, if the order of reactant A in this reaction is 1, that means that the rate is directly proportional to the concentration of A. So when I increase concentration of A, as we go to the right, our rate will increase linearly in a straight line. And this is because the proportionality is 1. or to 1 of the concentration of A. And this is because when we plot the graph, right, we essentially make it y equals mx. And if we know a little bit of our math, we know that x would be A and y is rate in this graph. And since k is a constant, so m is a constant, and therefore the gradient is a constant. Now we move on to the concentration versus time graph. So what's unique about this graph over here is that while the concentration of A or the reactant will decrease as time proceeds as expected, it would decrease not linearly because the gradient of this graph, the rate, decreases as time decreases. And this makes sense because the concentration of A decreases as we proceed in the reaction, and therefore concentration would affect the rate. If the concentration of A decreases, the rate would decrease. And because the rate decreases, your gradient in this graph is going to decrease as time decreases. And therefore, the slope from steep will get gentler and gentler. Now, there's another interesting point to note for first order reactions is that the half-life is always constant. The half-life is the time taken for the concentration of reactant to decrease to half its initial value. So if I have a starting point, let's say at 100% over here, the time taken for it to go from 100% to 50% should be equal to the time taken for it to get from 50% to 25%, and it should also equal to the time taken to get from 90% to 45%. That is the unique pointer about first order reactions. The half-life is always constant. Now if we move on to second order reactions or above, in second order reactions, the rate would increase not linearly anymore because we have a rate against concentration, and this is pretty much equal to a y equals mx squared. And if you know from this, this is an exponential graph. And if you look at a concentration versus time graph, it is similar to a first order reaction because again, the rate would decrease as the time decreases, in fact to a greater extent than your first order reaction, right? So your gradient will also decrease to a greater extent. And you can see a sharper change in the gradient itself. And therefore, your graph would look something like this. And in this case, for second order reactions and above, it doesn't have the constant half-life theory. Now just take note that your half-life in a first order reaction can be defined in this equation here. Please memorize this equation. It's very useful for your calculations and exams love to test this. Now we move on to pseudo first order reactions. Pseudo first order reactions are, in the name itself suggests that they're not really first order reactions, but experimentally we have a way to make it such that it is a first order reaction. For example, in a typical reaction where A plus B gives C plus D, if B is in large excess, a change in B can be considered as negligible, and thus your Kb can be estimated as a constant. If you look at the equation for the reaction, let's say the rate is equals to K concentration A and concentration B, that means it is a first order to reactant A and a first order to reactant B. Overall, it is second order. But in order to make our experimental conditions simpler, we can make B in large excess. And in this case, when you make B in large excess, a decrease in A wouldn't be not really a decrease in B. It is a very, very small decrease. And therefore, you can pretty much assume that K concentration B in this equation would be estimated as a constant. And we can represent this as K prime. And therefore, our new rate equation would be rate equals to K prime times concentration of A. And in that way, we have just made a second order reaction similar to a first order reaction, or what we call a pseudo first order reaction. So this is important to know because experimentally, we usually do not want to vary the concentrations of different reactants at the same time. So what we will do is make one in large excess and try to identify the order of the other reactant first, and then vice versa in a subsequent experiment. There are other ways to make it a pseudo first order reaction. It's when the solvent is a reactant. In this case, you're also making it in large excess as well. Or when there's the presence of a catalyst, again with the large excess theory at the same time. I'm not going to dwell too much details into this. What's more important for you to know is how to derive this pseudo first order reaction and the theory behind it. Now moving on to some experimental methods for studying reaction rates, we have continuous methods. So these methods, not going into too much details, these are ways to calculate the rate as the reaction proceeds. And you're always taking readings at different timings of the reaction. This is versus a clock reaction where you would get to try this in the practical. This is where you typically have a cross drawn on a piece of paper underneath a conical flask with the reaction mixture, and we try to look down from above, and as the reaction proceeds, you time, and when the cross suddenly disappears from your vision, you stop the time. So clock reactions in that sense are a good way of taking the time taken for the concentration to reach a certain point, in this case when the cross disappears. So this is good for reactions where the concentration reaches a certain point, the reaction gets too murky, right? And you cannot see the cross. And then in this reactions itself, you would estimate the rate to be equal to 1 over time. Now we move on to reaction mechanism. Reaction mechanism are ways to determine how a reaction occurs by showing step by step how the reactants become products. And in all of these steps, there's always a rate determining step. As the name suggests, this would be the slowest step in the whole sequence. And because it is the slowest step, it pretty much determines the overall rate of the reaction. This slowest step, or the rate determining step, is usually the step with the highest activation energy. If you look at a typical energy profile of a multi-step reaction, from the reactants, you go one step using activation energy 1 into an intermediate or transition state. Here I will call it intermediate. And then you'll go through a second step down all the way back to your products. And you just have to take note when you draw these multi-step energy profiles that the rate determining step has to have the highest activation energy. Next are factors affecting the rate of reaction. So in order to understand what makes up a reaction within your reaction or within your system, you have to know about effective collisions. Effective collisions are when reactants have a minimum energy, which is an energy greater than activation energy, and the reactants must collide in an exact orientation for the reaction to occur. With these two conditions, we can think of the factors that will affect any of these two conditions. So this is a summary of all the factors that affect your rate of reaction. We can start with temperature. So temperature increases your average kinetic energy of your particles. Because of that, the number and fraction of reactants with energy greater or equal to activation energy will increase. You also increase the collision rate. And when you increase collision rate, you effectively increase your effective collisions between your reactants. Now we look at concentration and pressure. For pressure, it's only for gases. So for concentration and pressure, you are increasing the number of moles of reactants per unit volume. In that sense, you are increasing the chances of collisions itself. And therefore, your number and fraction of reactants with energy greater or equal to activation energy increase. Therefore, the frequency of effective collisions would increase. Now how about catalysts? So catalysts provide an alternative pathway with lower activation energy. And because of that, when you lower activation energy, the energy of your particles, the fraction of your particles with energy greater than activation energy will increase, and therefore leading to more effective collisions. Lastly is surface area. Surface area is when you have powdered solid reactants compared to blocks of solid reactants, and these have high surface area to volume ratio. And because of that, you definitely increase the rate of collisions and therefore the rate of effective collisions. So take note that surface area does not affect any fraction of particles with activation energy itself, and goes directly straight to this explanation. When you have rate of effective collisions increase, you will therefore have a rate increase. So do take note in your explanation that you have to follow this series of steps when explaining in order to show the examiner that you understand what comprises of a successful increase in rate of reaction. Let's move on to the Boltzmann distribution curve. So I've drawn the Boltzmann distribution curve for you. Typically, we would show the one in blue first. So this is a typical Boltzmann distribution curve, which shows the distribution of energy with your particles. And then you have a certain fraction of reactants with energy greater than activation energy. So that will be shown in blue over here. And then what happens when you increase temperature? When you increase temperature, if you look at the red line and you draw the additional area that is in red, the proportion of reactants with energy greater than activation energy would increase, and therefore your rate of effective collisions increase as well. So what happens when you add a catalyst? Remember, a catalyst only lowers the activation energy of a reaction by providing an alternative reaction pathway. Therefore, your activation energy would shift to the left. And therefore, in itself, you can see that the proportion of reactants with energy greater than activation energy increase, shown by the blue area and the green area. So the Boltzmann distribution curve is a very good way in explaining why the proportion of reactants have energy greater than activation energy, and how the factors of temperature and the catalyst would influence the proportion of reactants with energy greater than activation energy. Just a side equation, you can write the rate constant Arrhenius equation, which is K equals to AE to the power of negative EA over RT. So this is a constant for this equation, and sometimes questions would ask just to see if you do remember this equation. So just use this for your calculations. Now we move on to a big concept, catalysts. So what are catalysts? Catalysts increase the rate of reaction by providing an alternative reaction pathway with lower activation energy, and they remain chemically unchanged at the end of your reaction. So there are two kinds of catalysts. You have to memorize these two. One of them is a heterogeneous catalyst. This one is when the catalyst and your reactants are in different physical phases. So if you look at this diagram, this shows the necessary steps in order for your heterogeneous catalyst to work. If you look at step 1, this is diffusion. This is when your reactants, let's say A and B, start to go towards the catalyst. And then we look at step 2, which is adsorption. Adsorption is when your catalyst forms these weak intermolecular forces with your reactants itself. So they kind of act like a sticky surface for your reactants to stick to in the correct orientation for reaction. And then we move on to step 3, which is the reaction itself. So the sticky surface will provide the correct orientation for your reactants and also lower the activation energy for the reaction to occur. And then for step 4 and step 5, this is desorption, which is removing the stickiness, or the product itself is being removed from the catalyst surface. And then for step 5, which is diffusion, where the product says bye-bye and goes off away. This way, a new set of reactants can come to the catalyst surface and ready for a new reaction itself. And do take note that the catalyst also remains chemically unchanged at the end of this reaction. So just to run through again, please memorize all the explanations for a heterogeneous catalyst. Exams love to test this 3-mark question related to a heterogeneous catalyst itself. So remember that 1, your reactant molecules diffuse towards this solid catalyst. 2, they are adsorbed onto the active site, so keyword, of the solid catalyst by intermolecular forces of reattraction. So this will increase the local concentration of your reactants. And then step 3, you have a chemical reaction, and the reaction will have a lower activation energy. And then step 4, your products break away from the catalyst surface. And step 5, your products diffuse away from the catalyst surface, and the active site becomes vacant for your next reaction. or for new reactants to come in. Next is a homogeneous catalyst. So these are reactants and catalysts in the same physical phase. And in this case, the catalyst just provides an alternative reaction pathway with lower activation energy. And you would form an intermediate in the middle, and your catalyst is regenerated at the end of the reaction. This is usually possible because catalysts in this case have variable oxidation states. So if you look at a typical example, which I don't really want to say you have to memorize it, but it'd be good to memorize this sort of reaction can work. I'm talking about I- and S2O8 2-. And this is because these reactants always come out, and I mean always come out, somewhere in the practical or somewhere in the MCQ or somewhere in your open-ended questions. So how this reaction works is normally your S2O8 2- and 2I- would be able to react. Thermodynamically, it's able to work. However, kinetically, it's not going to be possible, or more like it's going to be very slow because your two reactants are negatively charged, as circled in red. And as we all know, negative charges don't really like each other and would repel each other away. Therefore, your rate of reaction would be slow. However, with the use of a catalyst, in this case, your Fe2+ over here, you can undergo a multi-step reaction that is an alternative reaction pathway. So what Fe2+ does is it acts as a positively charged cation that would react with each of the reactants separately. So in your step 1, your Fe2+ reacts with S2O8 2- to give one of the products. And then in step 2, your Fe3+, which was generated from step 1, this is actually the intermediate. This intermediate would react with I- to give your second product, and it would regenerate the catalyst. So why does this reaction give a lower activation energy? It's because your Fe2+ is positively charged. And with this natural attraction of the positively charged Fe2+ with the reactants itself, which is S2O8 2- and the I- later on, you can get a reaction with much lower activation energy. And because of that, your reaction will proceed much faster. Next up, we move on to autocatalysis. Autocatalysis is also a special reaction type that we start to learn in JC. This is where the product of your reaction is a catalyst. And as you can already tell, because if the product is a catalyst of the reaction itself, your reaction is just going to speed up as we go along. So it's initially slow due to the lack of a catalyst, and then as my reaction proceeds, the rate will increase exponentially. And then it will come to a point where the rate reaches a maximum stage. And this is because there aren't enough reactants to occupy the active sites of your catalyst. Because of that, the rate slows down slowly as the reactants start to deplete. If you look at this next page, this is a typical graph of an autocatalysis reaction. So we start with a very slow initial rate, and then it starts to increase in rate. Looking at the gradient, it becomes steeper and steeper until it reaches a maximum, because that is the point where all your catalysts and their active sites are saturated. And then the rate starts to decrease because your concentration of A, or the concentration of reactant, decreases to the point that not all your active sites are being used up. And lastly, I want to talk about enzymes. So enzymes are biological catalysts. These are the catalysts that are produced in your body and help to maintain your biological systems. From the name, you can already tell that these catalysts also provide alternative reaction pathways to lower activation energy. They are highly specific in picking your substrates, and in that sense, they are quite similar to your heterogeneous catalysts, where they have active sites and act as a sticky surface for your substrates, or what you call your reactants in the biological system. And through the use of enzymes itself, you're able to attain the fast enough reaction rate in your biological systems. Do take note for enzymes itself, as you increase the concentration of your reactant, the rate would increase, but to a certain extent, because of your saturation of your active sites. Very similar to increasing the concentration of your enzymes. It is the same principle. And also take note of a special feature of enzymes where they are very specific to temperature. And pH. So they operate in very, very unique circumstances and conditions. If the conditions vary even a little bit, the enzyme activity would decrease or increase depending on the change. So that's it for reaction kinetics. As I explained earlier, reaction kinetics is a very application heavy concept, and I would advise you do more practice for reaction kinetics itself and focus on how to apply the concepts in drawing the graphs and in answering questions. So if you like this type of content, make sure to hit the subscribe button so that you can get more frequent updates from this channel. And if you want to enroll in my online class, be sure to hit the link below so that you can book a free call with me and I can run through your past exam paper and clarify any doubts and explanations that you require. And I will also show you how my program is the best fit for you. I'll see y'all in the next lesson.